Okay, um, welcome everyone. We are resuming our mobile and wearable health seminar series for this academic year. And our first speaker is Jesslyn Dunn, who is an assistant professor of biomedical engineering at Duke University. She's the director of Big Idea Laboratory that has the aim to detect, treat, and prevent chronic and acute diseases through digital health innovation. So her research is very, very relevant to this community. Thank you, Jesslyn. Floor is yours.
Hey, thank you so much, Dr. Mascolo, for the invitation to speak to this audience. I'm excited to be here. I will introduce my lab and then I'll dive into the research that we're working on. So my lab is the Big Ideas Lab, which of course for any health related lab is an acronym. So we are the Biomedical Informatics Group. We integrate data engineering and analytics. And as Dr. Mascolo mentioned, our overarching goal is to develop and test tools and infrastructure using biomedical and health data for early detection, intervention, and prevention of disease. So today I'm going to cover a range of topics. And what I hope that you take away from this talk is first, just getting a view of the landscape of existing wearables today, their history, learning what I mean when I say digital biomarker, understanding where data comes from and how it flows through devices to get into our hands, learning about the methods that we use to evaluate wearable devices and decide how to handle the data generated from them, being aware of some of the challenges that come with collecting that data, a lot of practical challenges that we need to develop new methods to overcome. And I'm hoping that people on this call will be excited and motivated and perhaps want to address some of these challenges. And then I'll talk about just one real world application of digital biomarkers for infection detection. So to dive right in, I think if you're on this call, you probably already have a hunch for why wearables. But we know that we have these devices that are on people's wrists, sometimes in their earbuds, sometimes on necklaces, jewelry that are continuously measuring biosignals seamlessly in the real world. The measurements we have seen are more consistent than in-clinic measurements. So you can see here, one of the analyses that we did was over about 50 people over the course of a few years, comparing measurements that were taken in the clinic with measurements that were taken from their smartwatch. And as you can see, there's this very clear circadian pattern, no matter how you slice and dice the data. So whether it's people at rest, whether it's people who are moving around, whether it's longer or shorter time windows, there's a very clear difference in heart rate throughout the day. But if you just take clinical measurements, you miss that intra-day variation. Because wearables measure things throughout the day, we can actually capture that circadian information. The other valuable information that we get from wearables is that we learn intra-individual patterns. So we know that we have normative values based on our sort of analog methods of measuring people, which is one measurement maybe every 6 months to every few years, and that nobody really is the average. And so what the wearables do is give us this opportunity to learn how a person is changing based on their own baseline. And so wearables provide this really powerful source of data for us to learn about people's health. And not only are they powerful in terms of the data, but also the form factors are expanding enormously. So on the left here is just some examples of the types of body systems that we can measure from wearables. And on the right, I'm showing various form factors that used to be more futuristic, but are really becoming more of the norm. So we think about smart textiles, we think about paintable or tattooable electronics that can really enable this continuous monitoring without people having to remember to put a device on and off, without having to remember to charge it. So there are innovations taking place in miniaturization and battery and types of biosignals that can be measured. And all of these innovations together are giving us this huge opportunity. And just one example of a real world application, for those of you who follow the continuous glucose monitor, we had a huge breakthrough over the summer where this CGM was available over the counter for anybody to purchase in the US, which is a really huge hurdle for something like this to actually be able to do. And looking back at the history of this, if we look back to 1960, where the first blood glucose measurement was taken on a device that looks like this, down to 60 years later, this is the device. It's pretty incredible what the technological advancements enable us to do. So this is one of infinite possibilities of things that we could measure. And so I want you to sort of have this framework as we go through and thinking about the smartwatches that we're using and thinking about the different tools where we're collecting biosignals, that a lot of this in terms of form factor is only the beginning. And again, this we don't expect to be the end, but it's a pretty good place for us to be. So with that, I will dive into describing in more detail what digital biomarkers are, some more details about the challenges that we face when we're trying to develop these digital biomarkers, and then give a real-world example of how this can be used in practice. So with all of these wearables, we have a massive amount of data that gets generated. You might think, for example, that we have a smartwatch that's measuring, say, 4 different biosignals, maybe at 100 hertz each, and that we could have those measurements over many years. All of a sudden, if you scale that up to a population of hundreds or thousands of people, you can envision how this data footprint just grows. And so the question becomes, well, how can we leverage that data to actually make actionable insights, given that we have so many measurements that need to be brought together to make sense? And so the solution here is a digital biomarker. And we can use the traditional definition of a biomarker to better understand what we mean by a digital biomarker. So a traditional biomarker has kind of these two overarching uses. One of these is diagnostic capabilities. So this idea that we might be able to track intermediate markers of disease or treatment progress. A great example of this would be in the diabetes space. If we think about fasting plasma glucose, that's a measurement of blood glucose when somebody hasn't eaten for at least 8 hours. And we could use that measurement from a blood sample to say whether somebody likely has pre-diabetes, type 2 diabetes, or is normoglycemic. And then if they have type 2 diabetes, we might give a medication, metformin, for example, and then we can use that fasting plasma glucose measurement to track treatment progress. So if we intervene, how does that biomarker change? The other thing we can consider biomarkers to be useful for is actually learning new things about physiology. So for example, we might do a large-scale biomolecular analysis, like shotgun sequencing, for example, where we learn new associations between biomolecules and an outcome of interest. Maybe that's diabetes. So what we might learn is that there's a new mRNA or there's a new biomolecule that wasn't formerly known to be associated with this disease outcome. That enables us to learn things about phenotype and biological function, and also identify putative drug targets that can be used to improve the disease state. So this concept is exactly analogous to digital data. Rather than taking a blood sample, like a fasting plasma glucose measurement, we're taking a digital sample. So what we're doing here is we're taking digitally collected data. That could be continuous location data from a smartphone GPS. That could be heart rate, temperature, a variety of different types of digital measurements that we transform mathematically into indicators of health outcomes, like infection or diabetes. So you can think of this as sort of akin to an economic indicator, that we have a lot of continuous data coming in, and what we want is a snapshot or a picture of what's going on with a person's health. And we can functionalize this. So we can create these relationships through mathematical equations to say we have a variety of different signals that are being taken in, and we want to relate those to outcomes of interest. These could be clinical measurements like fasting plasma glucose that I've used as an example. And we actually have a study that I don't have time to talk about today where we do exactly that. These target outcomes can be anything that's currently used in clinical practice or in healthcare to make decisions about people's care. And what we want to do is develop ways to do that using ideally non-invasive and passively collected data. So some examples of questions that we could ask in terms of digital biomarker development are, can we develop digital biomarkers to detect whether somebody is susceptible to contracting illness? So we may, for example, have a constrained setting where we have a group of people that we need to send out into the field and we know are going to be exposed to some contagion. How do we select who of those people might be least likely to contract that contagion? Or vice versa, if we have a group of people who are all sick, but they have a unique skill set and we need to send somebody out into the field, can we actually learn how contagious a person is based on their biosignals? We're looking at other topics in my group as well, including looking at cardiometabolic diseases, prediabetes, type 2 diabetes. We're looking at more general health, how exercise and sleep relate to chronic conditions. And we're doing some studies in shift workers, looking at circadian disruption. We're working with women's health and preterm birth. And broadly, there are, incredible amounts of questions and lots that we can learn through this lens of developing digital biomarkers to relate to health outcomes of interest. So there's a lot of potential here, but there are also challenges that come with trying to answer questions like this. So some of the challenges that I'll list out here are in knowing that the data that we get from the devices that we're using are valid and accurate. A phrase that we like to use is fit for purpose. So knowing that the thing that we want to measure is the thing that we're measuring. Interpretability and fair principles. So when we're actually leveraging this data and developing algorithms, are those algorithms interpretable and explainable? Is the data underlying those algorithms made available such that people can better understand the limitations of that algorithm performance? We're working again with massive amounts of data. It's different than a lot of the other use cases where massive amounts of data exist, like genomics or even the physics world, because we have not just these snapshots in time, but rather these very continuous signals that are being taken simultaneously on many different sensors on very large populations. So learning how to make sense of that is really critical. I'm not going to discuss today regulatory oversight because there's a lot going on in this space. It does tend to be more specific to certain geographies. And so I think, that's just a note that I want to make, that it's important to consider whatever environment that you're working in, what the regulatory climate is for those tools. And there are lots of issues that relate to privacy, security. We have this phrase ELSI, ethical, legal, and social issues. And all of these come into play when we're thinking about how not only to develop digital biomarkers, but how to implement them in practice. So I want to start by talking about this question of data validity and accuracy and diving more deeply into the method of measuring heart rate from a smartwatch. So many people, I'm sure, have seen, your general smartwatch. You usually have a green light on the back of it, a green or a red light, usually a combination of both these days. And what that's doing is actually passing light underneath the skin. And in general, the smartwatch form factor actually has a light path and a photodetector to detect absorbed light or whatever light gets passed back through the skin. And the beauty of this is that there are differences in the absorption of light when there is more or less oxygenated blood. So with a pump of the cardiac cycle, you get a bolus of blood that comes through the microvasculature that has a change in absorbance. And because of that, you can see this oscillatory pattern of absorption that relates to the heartbeat. So the proxy basically for heartbeat ends up being this light absorption signal. Interestingly, there are other things besides oxygenated hemoglobin, oxygenated blood, that absorb certain spectra of light. The green light tends to be the one that's used most commonly because it has the best absorption for oxygenated hemoglobin, but melanin is also a biomolecule that absorbs the green wavelength of light. So this was a question that has been brought up, lots of anecdotal evidence that there were challenges with measuring heart rate accurately in people with darker skin tones, so people with more melanin in their skin. And so there's this broader issue of signal to noise ratio when it comes to optical heart rate monitoring. And the questions that are being asked are, does the heart rate monitor work across diverse skin types? There are other sources of noise that can also exist, such as motion artifacts. Depending on where the device is placed on the body, you may have more or less perfusion under the skin and therefore a more or less signal that could get in the way of getting a good measurement. There's also potentially an issue of a crossover problem. So if you've developed an algorithm that's locking on to a periodic signal because that's the expectation of the cardiac cycle, and you have somebody who's actually walking on a periodic cycle, you could have your algorithm lock onto the wrong periodicity and therefore choose the wrong thing to be heart rate. So the take-home message of this, and I'll talk about a study that we did, which actually looked into the first two issues, is that tuning hardware and software simultaneously is very important because a lot of the issues that we have are not only hardware problems or not only software problems, but are actually a combination of the two. So we set up a study several years ago to ask this question in the commercial smartwatches that were available at the time. Are there problems with the heart rate and heart rate variability measurements that we get across diverse skin tones and under different sorts of motion artifacts? And so you can see that the study set up here, the numbers in the people indicate how many people within each of these skin tone categories were in our group. We use the Fitzpatrick skin tone scale here. We know that that's imperfect, but 5 years ago, this was kind of the state of the art. We had several different activities that people could take part in. And then we had what we were referring to as our reference standard measurements, the clinical metrics using ECG. So we had our PPG-based devices here. We had our other PPG devices that were research grade. And one of the questions in our mind was whether we would potentially get better signal from research grade devices. And we compared the measurements of heart rate and heart rate variability to ECG as a reference standard. We were glad to find that there was no change in accuracy based on skin tone. We had expected that there might be challenges, and one of the hypotheses that we're currently testing is whether the LEDs are actually tuned up to have higher intensity for different skin tones to be able to overcome this issue of melanin absorption of that green wavelength. We also know that there are multiple new wavelengths or different wavelengths that are being integrated, which can also help to overcome that issue. But concerningly, one of the big issues that we found was that with these devices, the accuracy in heart rate and heart rate variability measurements drops dramatically during low intensity activity. So the highest intensity activity we had people doing was walking on a treadmill at, a fairly slow pace. So the question becomes, in this idea of fit for purpose, well, if you're using these devices to try to measure somebody's heart rate changes during exercise, for example, for an exercise stress test, is your device fit for purpose? Is it measuring what you think it's measuring? And if our accuracy decreases so dramatically during activity, then the answer is probably not. So this gets to this question of making sure that the devices that are being used under certain circumstances are validated for those circumstances. And that's just a very brief overview of ways to be thinking about data and device validity and accuracy. We've worked with the Digital Medicine Society to develop this framework that we call V3, which is verification, analytic validation, and clinical validation, which helps to kind of think through, how do I know that my device is fit for purpose? So if you have any questions about that, I'd be glad to distribute materials about that after this talk. I want to move ahead to this next question of interpretability. And I'm going to frame this in the sense of currently existing wearables that are on the consumer market. I imagine that most people on this call have seen some of the most current smartwatches that have a variety of algorithms that already exist on these devices. Whether it's being calculated on the device itself or on, a smartphone or server. The bottom line is what these are doing are taking in signals from the sensors on the device and are applying algorithms to do decision making. So some examples of these are irregular heart rhythm detection. We've seen, several examples, and this is not an exhaustive list. Again, I'm just showing snapshots of some of the more common ones. We have fall detection and crash detection, sleep apnea and stress detection are some of the newer ones. But ultimately, some of the challenges with this is really understanding what's going on under the hood and how we're going from these continuous sensor measurements to a decision like this. And some of the ways that this can become very important are in understanding where the algorithms fail. What are the false positive and false negative rates, and what are the consequences of those? And so, a good example of this was for this crash detection. This would have been 2 years ago. The Apple Watch had a problem where in skiers, it was detecting that there were crashes and it was automatically calling the emergency lines and clogging up the emergency lines. And so emergency responders would go out to the slopes, and it turned out that people just didn't know because they were under all of these clothes that their watch was calling emergency responders. And in some cases, actually, the emergency responders stopped going to the slopes because it was clogging up their systems and there were too many false positives that really caused real problems. So it's important to think about when you're deploying algorithms, what are the points of failure? And a lot of times there are going to be unforeseen points of failure, and so being able to be agile and respond quickly is important. One of the types of algorithms that's really near and dear to my heart, because this is something that we've been working on very closely in my lab, is this idea of detecting anomalous health conditions, which we specifically think about often as infection. And there are a variety of general algorithms that are out there these days. Apple has one called Vitals, Whoop has Recovery, Aura has Symptom Radar, which actually just a couple of days ago was taken offline. And then Garmin has this body battery. And all of these are pretty general. And again, the questions become, well, what's going on under the hood? What types of decisions are being made and why? And one of the areas that we've been working toward is trying to open up a lot of these digital biomarker algorithms. So we have an open source software project called the DBDP. This is an open source community that anybody can join and contribute to. So I would encourage you, if you're interested in this, to check out dbdp.org. Where we have data, code, algorithms, and educational resources on this algorithm development, leveraging wearable sensor data to make decisions about health. And this community that we're building is to try to leverage each other's work such that we're not always reinventing the wheel every time a new technology comes out or a new question is being asked about how to use sensor data. So there are a lot of common modules that are being used here. The data preprocessing is a very popular module, and as is exploratory data analysis. So this is plugging in continuous data and seeing what comes out of it. And then we also have algorithms for calculating heart rate, resting heart rate. Glucose variability is also a very popular one using continuous glucose monitor data. And with this, there's a lot of documentation. So if you have any questions, this community is really active and excited about building up a digital biomarker discovery community. So if you want to contribute code that you've written, if you want to build upon other code that exists, there's information on how to do that. And I encourage you to please reach out if you would like to get involved. So one of the other challenges that I brought up in this space of digital biomarker development is massive amounts of data. And so we've talked about digital biomarkers as being one of the solutions to this. But it's not the only solution. And there are other ways that we and others have been thinking about addressing this challenge of lots of data. So this slide is a bit outdated by this point, but the idea here is that the amount of data that we have has already exceeded 2,000 exabytes. We have massive amounts of data that actually have a physical footprint, right? This data exists on servers somewhere. And so it's, living in this sort of cloud era, I think a lot of times it's easy to forget about the physical footprint that data takes up. But we can also think about the downsides of collecting massive data in that on devices, it kills battery, right? So the more that we collect, the more it drains battery, the more people need to take the device off and might forget to put it back on. And so we've been asking this question of how we can minimize data volumes while maximizing the accuracy of the digital biomarkers. So ensuring that the data is fit for purpose while trying to minimize its storage footprint and the amount of data that needs to move from place to place. So we could just reduce the amount of data that we collect. So we could reduce the frequencies of data collection from 100 hertz to 50 hertz. And we can determine where that line is where we start to lose accuracy in the digital biomarkers. We can also develop some application-driven compression methods. And for time, I'm not going to be able to dive into the details on this, but one of the things that our group has done is leverage the oscillatory behavior of some biosignals to develop better compression methods that can allow for lossless data compression that reduce that storage footprint. And then we could also intelligently aggregate data. One of these ways is developing digital biomarkers. And so if we think about just this idea of reducing the amount of signal level or raw data that we collect, we can take the example of the ECG that, let's say, is collected at 1,000 hertz. If what we care about is heart rate or heart rate variability, what we really need are these peaks. And so you could imagine reducing the frequency of the signal that you're collecting or the sampling rate such that you can still capture those peaks. And what we did was we compared if you are to have this signal, cut it in half, and where do you end up actually losing the information that you care about? So if we look at heart rate variability as an example of this, we can start with the highest resolution signal that we had here. This was PPG at 64 hertz. And you can see that if we cut that in half to 32 hertz, or if we cut it in half again, the signal that we measure for HRV is not statistically significantly different from the first signal that we started out with. When we start to go farther than that, that's where we start to really lose information. And so what we can see is that we can already reduce our data volume by quite a lot. And this actually has real world implications. So if we look at the amount of data storage that we would need to have in terms of a footprint on a server, we can see that if we go from this 1,000 hertz ECG down to a 64 hertz PPG and then kind of continue to cut that in half, the amount of storage required is dramatically lower. And if we actually look at that in the cost in dollars here, we can see that this saves substantial amounts of money. Even going from 64 hertz to 21 hertz, we're going from, $7 per user per year down to $2 to $3 per user per year. As you start to scale up to many people and many years, this really starts to have an effect. So it's very useful to kind of know where are these limits to the amount of data that I need to collect given my goals for my analysis, and can I reduce the cost of a study based on that? So that's I'm going to stop there with the challenges. And again, I mentioned that there are two other areas that I'm not covering in this talk on the regulatory issues as well as the ethical, legal, and social implications. So these are topics I also care a lot about. I would be glad to discuss further at any point in time. So again, please feel free to reach out to me if you would like to talk further about that. I do want to make sure that we have time in this talk to talk about a real world application of digital biomarkers. And I'm going to frame this through three different stories. One where we talk about the basis of the idea, one where we talk about the idea in a very controlled laboratory setting, and then one where we talk about the idea deployed in a real world setting. So the work in detecting uh, anomalies from wearable devices actually began when I was a postdoc working with Mike Snyder at Stanford. So a giveaway here is that we found some pretty cool results when we started analyzing data collected in a cohort of individuals that indicated that there are signals that indicate infection or illness before a person might actually feel sick. So I'm going to tell you how we did that. We had 100 individuals over the course of several years. I think the study has now been going on for more than 10 years, so it's really been quite a while. At the point when I was analyzing this data, it had been going on for roughly 5 years. And in this study, people are coming into the clinic 4 times per year to give biosamples. And they're also about half of this population was wearing wearable devices. So you can imagine that this data collection started back in 2014. So we had, this was the early days of smartwatches. We were using the Intel Basis watch, which is no longer on market, but it was collecting a lot of the same signals that we would see in the Apple, Fitbit, Garmin, Samsung, you name it device today. What was really fascinating about this was that because people were being monitored over the course of several years, they had these kind of natural perturbations that would take place. There were a couple of people who ended up having stressful life events, some people who stayed up for 48 hours for, various reasons. And we could actually look at what those biosignals looked like and compare them to biomolecular signals, which was super cool. The viral infection was some of the most fascinating work because when people got sick, they would come into the clinic and give more high density sampling. So we would have the matching clinical measurements with the wearables measurements. So if we were to look at just the general data for this population, we can see that in red here, I'm showing heart rate, and in blue, I'm showing skin temperature. And these black boxes here are showing the amount of time monitored. And this was 43 people out of that cohort that wore their devices with some consistency. What you can immediately see, first of all, is that your temperature doesn't have super high variation, which we would expect because knowing sort of the dynamic range of body temperature versus heart rate, body temperature really can't vary that dynamically and have somebody still be alive and healthy, whereas heart rate has a much wider dynamic range. And so what's kind of interesting, so each of these verticals is one person, right? So if we were to look at let's say comparing a person here and a person here who have roughly the same average heart rate, but we actually look at the variance of those individuals. For this person, if we have a measurement that's in sort of like the mid 80s to low 90s, that's totally normal for this person. They have just a high heart rate variance overall. But for this other person who has the same mean heart rate, that measurement would be very much outside of their norm. So this gets to the idea that no one is average, right? We have these average values, but if we just compare measurements to an average, we miss a lot of information. Knowing intra-individual variation is also really critical. And we can see this example play out further if we look at circadian differences, for example. So this is the same population, and now we're seeing this is a change in heart rate. So we know that as people sleep, their heart rate dips down, their skin temperature tends to increase, but these changes are different for different people. And in fact, we see some people who actually have the opposite of what we might anticipate, right? And so this starts to get to, well, if somebody is outside of a population norm, does it indicate illness? Does it indicate natural, healthy intra-individual variation? And where are those lines? So what we decided to do was leverage people's own baselines to start to try to discover anomalies within an individual. And the way that we did this was the development of an algorithm that could actually take every measurement from a sensor and bin that measurement to say how normal or abnormal is this for an individual. So we have these bins that are within one standard deviation of the mean. And you can imagine if we have 64 hertz signals that we're getting for a day, 86,400 measurements from a specific sensor. We expect there to be noise in those signals. We expect there to be anomalies in those signals. How many anomalies, what proportion of the signal is anomalous gives us an idea of how true that the anomalous measurement is. So if we see blips on the radar here, where we have the size of the circle corresponds to the number of measurements in that day that are more than 2 standard deviations outside of the mean, either above the mean or below the mean, we can start to see days that stand out against the background. So we can see an example of this here, and this was data from an individual in the study. This is about a year and a half worth of monitoring. You can see there was a period where they took off the watch, which we hate when people do that, but there's no data there. But there's this period here that really pops out where we've got these blips on the radar of a really high proportion of anomalous measurements. And looking back at the health record, we could actually match this up to a Lyme disease infection. And because this was a part of this study where people were coming into the clinic regularly, we actually had some really nice clinical samples that we could compare to. And we could see that there were differential white blood cell counts indicating infection. And actually, for this person, a positive antibody screen demonstrating with definitively that this person had Lyme disease. But from the watch data alone, we would have pulled this time period out as something being wrong for this person. Now, remember that in this study, we had people coming into the clinic not only when they felt sick, but also when they were feeling healthy, just for normal time point measurements of biomolecules. So on this plot, I'm showing all of the points in time that a person, this study participant that I showed on the previous slide, came into the clinic and gave a sample. And we're plotting this by the proportion of outliers from the smartwatch data. So you can imagine that every point on this plot corresponds with clinical measurements. And there's a clinical measurement called C-reactive protein, which is an indicator of general inflammation. And so what we would expect to see is that for the days where we have more outliers on both the heart rate and skin temperature dimensions, that those would be more indicative of infection and therefore would have higher CRP. And in fact, that Lyme disease blip on the radar that we see corresponds to those most outlying observations. But there are other outlying observations here. So we went back to the clinical record to see if there was any information that we could find. And we found that one of those days corresponded to viral infection as indicated by the individual themselves. But there were 2 other dates that actually had high C-reactive protein measurements, but that the person didn't indicate that they were sick. So the really exciting take-home message of this is that there's subclinical inflammation here that was able to be detected by the smartwatch data that the person themselves didn't even feel sick. So a question that we get a lot when we talk about this is, well, what does it matter? Are we causing, false alarms, or maybe not even false alarms, but maybe people are carrying some level of inflammation or infection, but there's really nothing clinically actionable to do about it. I think that question has become less common since we've experienced the COVID-19 pandemic, where we see that these subtle signs of infection can actually be really impactful when it comes to spreading contagion. So what I've showed you here is sort of the setup for the digital biomarkers of infection that we're continuing to work on now. We have 2 methods of doing this. One of them is in a very controlled laboratory setting, and one of them is in a very real world setting. So I'll start with the controlled laboratory setting. And we have this model that we use called a viral challenge study, where we have people who are healthy and actually volunteer to be in a study where they get exposed to a pathogen, and then we have wearables on them as well as biomolecular measurements that are taking place to look at the course of the infection. We are very grateful to our participants. We actually have a study going on right now where people are undergoing H3N2 influenza infection. They have about 2 days left of their monitoring period. And it's really, an incredibly unique circumstance to be able to see what an infection looks like, knowing the exact date and time of exposure to the pathogen. So in the first of these studies, we had data that was collected on PCR. We had observable and unobservable symptoms, and then we also had wearables data. And we developed two different modeling methods to say, one, can we just detect simply whether somebody is infected or not infected? And two, could we get more information about the trajectory of their infection based on early signs measured from the smart device? Um, and so you can imagine basically these come down to predictive classification models. And so I'm going to show on the next slide the results of those classification models. And if we are to look at predicting, I'm here showing only infection severity, but predicting the presence or absence of infection performed even better than the severity. And what we could see is that whether we're using multiple different viruses. So in this study, we had H1N1 flu and we had rhinovirus. And we could either combine them to say, is somebody sick or not sick, or infected or not infected, or are they infected with H1N1 versus rhinovirus, which is a much harder question to ask, but it's something that we're very interested in these days, particularly with the impending flu season and thinking about, does somebody have COVID? Do they have flu? How can we potentially differentiate between those? So you can see from the confusion matrices here that these models are imperfect, right? Looking at the off diagonals, we see that there are failures, but there are more successes than failures. And when we think about the real world implementation of this, we know that we don't need perfection. What we need to do is reduce the number of people that are spreading contagion. So that takes us to this real world scenario where what we're trying to do is we've got these individual baselines from smartwatches that people are wearing all the time. We're developing digital biomarkers from that to have early identification of acute and chronic illness. And we can employ this for a variety of different purposes, but in an ideal world, what we're trying to do is curb disease spread. The questions that we focused on, or that we're continuing to focus on for our current study, is early detection. So getting to those people who are either pre-symptomatic, even asymptomatic, which we've shown we're able to do, and also to monitor on a much larger population scale at a very low cost. There are other opportunities here for at-home monitoring, for triaging people, for delivering health information that are all opportunities to leverage our existing digital infrastructure. But our study, COVE-Identify, really focused in on these digital biomarkers that we could develop from data that we collected. The questions that we asked were who should be quarantined and or tested and when, and who will need specialized care resources and when. And we answered that through a variety of different digital biomarker development processes. So how susceptible is a person to infection? Do they currently have COVID-19 infection? Are there pre-symptomatic indicators? How contagious are they? We had, population level data that allowed us to answer some of these questions, and we're actually continuing on to get to some of the more detailed questions. So in the very first cohort of data we began collecting in March of 2020, we sent out sort of a huge blast of, to our communities and to sort of the broader community saying, we're trying to collect smartwatch data to better understand what it looks like when somebody has a COVID infection. We collected data from people who had negative COVID-19 tests. This could either be because they were sick with something else, because the test wasn't very good, and so they actually had COVID, but it showed up negative, or that they tested too early, or it could be true negative. So people who were testing for surveillance, or they thought they may have been exposed, or they were traveling. So I want to make it really clear that this is a mix of negatives. It's imperfect. The positives we're pretty confident in. But again, a lot of these positives were after the initial infection took hold, because as we know, these tests are lacking in sensitivity. So you may have to actually have the infection for a day or two before it would show up. And this is, again, the early days, March 2020, right? Early days of infection. But what we can see here is looking at just step count and resting heart rate simply from a smartwatch, that we have these changes that occur prior to the test date. Looking at this detection period, again, we know that somebody would not be sick 20 days before a test and then have these changes in their biosignals. But because this was such a delayed time period of testing, these detection periods look much wider than they actually should be in the real world. And one of the reasons for this was testing shortages. So we asked this question of, can we leverage smartwatch data in order to address this issue of testing shortages, to better allocate resources to people who are more likely to test positive? So I don't know how it was in the various places where you all are in the world, but where we were here, there at various points where there were outbreaks, we would go to our local pharmacy and there would be no tests left on the shelves for testing. And this is really problematic because we had a lot of waste in tests being used for people who maybe were less likely to be positive and really didn't need the test, and not enough testing of the people who would be positive and actually go out and spread. And what this looks like, if we were to actually formulate it into a mathematical question, is if we have a population by this number of people here, where we've got some positives in orange and negatives in blue, and we have fewer tests than we have people that we would like to test, how do we decide who to give the tests to? So by the random allocation method, if we were to just randomly give tests out, we would get an 11% positivity rate with this formulation. But if we can leverage some prior information to help us maximize the number of positives that we can catch from the smartwatch data, we can dramatically increase that positivity rate. So the way that this works, again, is leveraging these biosignals. We see that between the COVID negative and positive cases, there are some differences. But again, there are overlaps in the confidence intervals between just steps and just resting heart rate. So that indicates that we need a more nuanced machine learning algorithm that can better enable separation. So we performed a grid search across a variety of different possible detection windows and start dates and end dates of the evaluation period for various activity-based features, resting heart rate. We also looked at sleep. And we developed an algorithm that could actually successfully improve this allocation of tests. So the results here, I think the key take home is kind of in this these two grids here, which is that when we're working in a low number of tests here on the left-hand side, having an intelligent algorithm that can tell us how to allocate tests is very impactful. We can have a much higher positivity rate with our intelligent testing algorithm, ITA, than with our random testing method. As we have larger and larger numbers of diagnostic tests that become available, the intelligent allocation becomes less critical. So the value of this in the real world really lies in the early days or during outbreaks where resources become limited. And a lot of the work that we're doing right now, we're working with a US agency called BARDA, trying to amplify this work and better understand how we can design intelligent allocation in the early days of new pathogens. So the take-home results from this are that the intelligent testing allocation algorithm that we developed from smartwatch data results in a 6.5-fold increase in the positivity rate using the cross-validated training set, using an independent test set, actually from another institution, so completely independent data, we had a 4.5-fold increase in the positivity rate. And there are more details here about the features that were important. So resting heart rate and physical activity were both important. We saw changes that were quite early. And again, this is because a lot of this data was measured early on in the pandemic where there were testing lags. And it was interesting that we saw how when we would tweak different features from the device, we could actually have this trade-off between precision and recall that would enable us to tune how much we wanted to catch using these algorithms. And a really nice real world expansion of this is work that was done by a group in San Diego showing that if you look at the Fitbit data broadly from large populations, and this is across the US, you can actually see that there are signals in population level Fitbit data that indicate flu outbreaks before even the CDC, the US CDC, would have that data. And so, this really points to the possibilities for what we can do with wearables data in the real world to better be ready for future pandemics. And there's more to this. We have a lot of work going on in the diabetes space and cardiovascular disease and sleep and mental health. So this is just one real world application of where wearables can take us. So to summarize everything that we've talked about today, just to rehash what a digital biomarker is, this is digitally collected data that is transformed into an indicator of health outcomes. There are quite a few challenges to be discussed in this space and to be addressed. We have an open source community called the DBDP that's working to address this, and we can leverage digital biomarkers as early indicators of infection. So with that, there are many people who contributed to this work. The folks in my lab, our collaborators, our funders, two are missing here, NIH and NSF. I'm really appreciative to have had the chance to present all of this to you. Thank you.
Thank you very much for your talk. Audience, if you have questions, please put them in the chat and I will read them out and we'll discuss. And feel free to leave, of course, if over time. While I wait for questions, I have one. It's actually, if you want the references on slide 27, that's just for you, but it's related to your work on a sampling for the PPG. And I was wondering if you've tried this on data that is stable, like stationary, or if you have seen if this works also when someone is moving. I wonder if there's an effect. I think you might be muted.
Sorry about that. Can you hear me?
Yes.
Okay. That's a great question. And the answer to that question is absolutely yes. Motion artifacts or any sort of noise matter. So what we care about is the ability to capture these phenomena of interest given the real world's noise. And so you're absolutely right that this study that was done with people at rest. So if you wanted to do this in a real world setting, you would probably need to do the same thing using sort of the ambulatory ECG chest straps. And actually, in an ideal world, you would use the patches. And we know that there can still be motion artifacts that affect those, but it's to a lesser degree. But yes, I think that's absolutely true. So I wouldn't use the numbers on this slide as the ground truth for deciding what your sampling rate should be. It should be within the circumstances of use. So if it's people who are sleeping, this is fine. Otherwise, not so much.
Yeah. I thought so, but I wanted a clarification. Peter Charlton has put a question on the chat. How important is it to improve the accuracy of wearable physiological parameters versus exploring their potential applications?
Thanks, Pete, for this question. It's nice to see you on here. So it's a difficult question because we don't need perfection, right? I think, for a lot of the applications, like we showed for COVID-19 detection, there's going to be noise in the signal, and still we can distinguish between who's likely to be infected and not infected. However, when we start to get into more specific clinical applications, for example, if we look at these irregular heart rhythm algorithms that are deployed on smartwatches, we do want to make sure that there is high accuracy because the consequences of false positives and false negatives can matter, right? Either it's causing anxiety, mental health challenges that come with people thinking that they're sick. It can flood health systems. And vice versa, if somebody sees that they don't have a problem based on their watch data, but it's missed, then they may say, well, I've already been screened and I don't have it, no problem, and then they die of a heart attack, right? So like they're in thinking about what are the potential consequences of this method failing, and then deciding in context, we accept this risk to benefit ratio, right? And I think that's always going to be the case, is that the more inaccuracies there are, the higher the risk there is of failures. And if so, what are the downsides of those failures, and do the upsides outweigh that? Hopefully that answers that question.
Well, I hope so. And we're coming up to the hour, so that's a good time perhaps to